Hello everyone. Today we have lecture 39 and our discussion point or topic is oxidation of metals and alloys, and we will continue our discussion on Ellingham diagram. Last class we have seen how to plot Ellingham diagram, which is nothing but the plot between RT-LnPO2 considering 1 mole of oxygen is consumed for metal oxidation forming metal oxide, and the assumptions are metal is pure, metal oxide is stoichiometric, and the system is closed system, and the system is trying to reach equilibrium because the temperature of the system is kept fixed. And we are plotting RT-LnPO2 with temperature, and we could see that within a certain temperature regime the variation of del G naught or the RT-LnPO2 is linear to temperature, where del H naught is basically the enthalpy change which is constant for an oxidation process, and del S naught is the slope of that particular plot between RT-LnPO2 and temperature. And this has a positive slope because the entropy change for the oxidation process, we have also noticed that it is almost equal to minus of individual entropy of oxygen gas in standard state, and that is what an entropy of a particular component or gas is always positive, since there is a negative sign. So, that is what the slope becomes positive. So, now today also we started mentioning that at every point in that particular plot indicates a particular partial pressure of oxygen which is in equilibrium in that particular system. Now, what we can do, we can take values corresponding to each temperature on that line, and from that we can get PO2, but there is one interesting way to find out PO2 from graph without doing any much of calculation. So, we will explain that part today, and then we will get to kinetics of oxidation. So, today's lecture is lecture 39 and topic oxidation of metals and alloys. And we started talking about Ellingham diagram. And it is a plot between delta Z naught so this is we can write it to RT-LnPO2, which is equilibrium temperature. And we have also noticed in case of Ag2O how this PO2 is varying, and this PO2 reaches 1 atmosphere when this value goes to 0. So, that corresponds to PO2 equilibrium T equal to 1 atmosphere. Now, the plot between RT-LnPO2 and T is this, and let us say I am considering only one case, metal plus O2 equal to MO2, and let us say this is the 0 value, and which is equal to delta Z is naught. So, it corresponds to PO2 equilibrium temperature equal to 1 atmosphere, and that equilibrium temperature when PO2 is 1 atmosphere is this one. This is the T we are talking about. This T and this T both are same. Now, in order to find at different location, for example, let us say I want to find out PO2 in equilibrium with this oxidation reaction. So, I just corresponding value, let us say this value is minus 10 kilojoule per mole. So, I will just equate delta Z 0 equal to RT ln PO2 equal to minus 10 kilojoule per mole. So, it will give me some PO2 value. If you do calculation, you will get some PO2 value, which will be definitely 10 to the power minus some x quantity, and this is atmosphere. So, this will be definitely less than 1 atmosphere pressure. Now, in order to find out this P equilibrium, this is temperature, let us say T prime. So, this is equilibrium T prime. You have to do a lot of calculations, though it is a simple calculation, but still you have to do the calculations, but there is a way out, and from the graph you can find out what is this value. In order to do that, let me go back to one interesting equation, which is del G equal to V dP minus S dt. So, this equation is a kind of one of those Maxwell equations. Now, here I can do this particular, and this is valid for even if we are considering fixed composition and constant temperature and closed system, and this indicate equilibrium condition. So, now if I consider isothermal change, that means temperature is constant. So, that case I can find out if pressure P is changed from P1 to P2, I can find out what is going to be change in free energy. So, in order to do that, I will simply take this, since the temperature is constant. So, this part goes to 0. So, del G equal to V dP. If I integrate, so G I can say P2 temperature minus G P1 temperature equal to this for ideal system, ideal gas. For ideal gas, I can take it as RT P dP P1 P2. Now, since the equation of state for ideal gas is PV equal to RT for 1 mole of substance, 1 mole of gas. So, this will become RT ln P2 by P1. Now, so that means we need to know both the pressures and find out this difference, which is nothing but delta G P1 to P2 at a constant temperature. Now, if we take P1 to be 1 atmosphere, then I could see that RT ln P1 becomes 0. So, then I can say that G P2 temperature equal to G P1 temperature plus RT ln P 2 by P1. Now, since P1 is taken 1 atmosphere, so corresponding value, this value would become Z0 or not, which is the standard condition at that temperature, plus RT ln P. So, now that time this becomes G P temperature. So, at a constant temperature, if we change the pressure, so then free energy change, so this becomes, this would be equal to RT, I can say P. I can say that this is my equation, or I can say this is my equation. I can write this equation to be G T equal to G naught T plus RT ln P, and therefrom I can get this. Now, interestingly, if I notice that this value is also equivalent to, I can write it equivalent to delta G naught T equal to RT ln P. Now, if there are number of gases, that case, if I try to understand with respect to oxygen only, since in this particular oxidation process M plus O2 equal to MO2. So, this is the only gaseous phase. The other phase, of course, while derivation we take vapor phase, but that derivation is bit complicated, we have not considered in our discussion. But now, if I say that final equilibrium condition is given as RT ln PO2, which is the partial pressure of oxygen. So, this can also be written as PO2, partial pressure of oxygen. This is equilibrium at that temperature of consideration. So, now we could see that if I try to plot T versus delta G naught, and let us say I take T equal to 0 K, and then this value is the value corresponding to O2 equal to 1 atmosphere. So, this point becomes 0. So, delta 0 T can be 0 when T equal to 0 K or equal to 1 atmosphere. So, we are taking this condition at the same. So, this condition if we take, so this point correspond to G 0, this value, this particular point. So, the difference becomes 0, means we are taking this difference corresponding to 1 with a 1 atmosphere pressure. Now, at any temperature, let us say I take this temperature, and at this point I want to measure the partial pressure of oxygen in. So, what I have to do, I just have to draw a line like this, which is connecting the 0 point. So, that means slope, if I try to see, this is delta Z 0 T equal to some value. So, now if I try to take the slope of this particular straight line connecting the 0 point at 0 K, the slope becomes this becomes my slope, because this is 0 and this is del G naught T. So, this is the point. So, this slope becomes from this equation. If I see this equation, if I write it like this, So, this becomes my slope. This becomes my slope. So, this particular slope is nothing but R ln PO2. Now, I can take R, if I take SI unit, then 8.314 joule per Kelvin per mole. Now, if I take this particular temperature axis, let us say this is 0, this is some value. So, now I take an arbitrary scale. So, I take a line like this, which will be connecting this straight line, and here if I put PO2 equilibrium T. So, this particular slant line connecting to the 0 point at 0 K is indicating of PO2 at that particular temperature, because at that temperature the slope is nothing but this, and where just adjustment of R can give you the partial pressure of oxygen at that point. So, the same principle is applied here. Now, if I draw a diagram again with reference to this is 0 K, this is temperature. Now, let us say I take metal plus O2, this metal oxide reaction, this is the 0 point equal to delta Z 0 naught. Now, if I try to find out the at this point what is the equilibrium partial pressure of oxygen. So, I just draw this straight line connecting this with a 0 point, which is indicative of 1 atmosphere pressure of PO2. So, now this point, and then there is a PO2 line, which is like this. Now, let us say if I have to draw find out what is the equilibrium partial pressure of oxygen, I just draw this straight line connecting this 0 point and this temperature what we are considering, then if I see that this will be the PO2 at this temperature. Similarly, if I try to find out at this temperature, then this will be the point. This is the line which will direct towards this 0 point at 0 Kelvin. So, now you will see in an Elingham diagram that in the PO2 part there are some lines which are indicating of, there are some line which are having kind of appearance like this. And if we draw this, extend this, every time they are going and connecting the 0 point. So, this axis is nothing but PO2 in equilibrium for a temperature. So, at this temperature what will be the PO2? This will be the PO2 1. This is at this case, this will be the PO2 2. At this case, this is the PO2 3. So, like that way, without doing any calculation, I have to just look at the Elingham diagram, see those points in the PO2 scale. This is a PO2 scale, and these slash lines which are actually meeting to the 0 point on del G axis. So, those line indicates the equilibrium PO2 at that temperature where this line cuts the oxidation Elingham line. Okay. So, these are the PO2 scale. So, at this point if I see, this point is indicating of 1 atmosphere, fine. So, that way the scale has been generated without doing calculation. One way, another way to find out this equilibrium PO2 at this point, instead of looking at this, you can take the value x equal to delta Z0 naught T, which is nothing but RT ln PO2 1. So, then we can find out PO2, but without doing this calculation one can find out this, and the slope of this line is nothing but RT R ln PO2 1, and in this case the slope is R ln PO2 2. In this case the slope is R ln PO2 3. So, these 1, 2, 3 are the 3 different temperatures. So, these are the 3 different temperatures. This is T1, this is T2, this is T3. So, like that way you can read partial pressure of oxygen at any temperature on this particular line by looking at what you have to do. For example, unknown temperature, let us say this is the unknown temperature you want to find out, or let us say this is the, let us say 1200 Kelvin temperature. I want to find out what is the partial pressure of oxygen for that oxidation process. In this case it is metal plus oxygen equal to MO2. What you have to do, you have to just connect this and extend it and see where this line is meeting on this PO2 scale. So, that point is nothing but the partial pressure of oxygen. Why it is so? Because we could see that this particular equation is valid here also, and this particular equation is coming because of the very assumption that the one pressure is considered to be 1 atmosphere, and here one pressure is considered is here, this particular line is nothing but 1 atmosphere pressure. So, that is what whatever point you consider on this particular line, they will be nothing but delta Z0 T naught. Fine. So, this is one information you can get out of Illingham diagram, where you do not have to do detailed calculation. Without doing calculation, by looking at the scale of PO2, you can find out what is the partial pressure of oxygen at any temperature on that oxidation line by just connecting the 0 point at 0 K on the RT ln PO2 axis and stretching it to the partial oxygen scale and see where it connects. So, that point indicates the PO2, because that comes from the slope of this particular equation, that slope tells me what is that PO2, and since R is a constant, that is what we could construct that scale. So, this scale was done by Richardson. Okay. So, that paper, if we see that paper, this is a seminal paper on that, F. D. Richardson and J. G. Jeffers, the thermodynamic of substances of interest in iron and steel making from 0 degree Celsius to 2400 degree Celsius, and this was published in Journal of Iron and Steel Institute 1948, and this was a seminal paper by them, and where the scale was drawn. See, there are other scale in the Illingham diagram also. You will find CO2 scale, H2O scale, but since our consideration is only oxidation in presence of only oxygen, that is what we are only indicating PO2. So, now what is the benefit of this oxide scale, this oxygen partial pressure of oxygen scale? Now, let us understand that benefit. So, let us say I have this particular RT ln PO2, which is nothing but delta Z naught T. This is 0.1 atmosphere. Now, let us say there are 2 oxidation process. In this case, this is M N plus O2 equal to NO2, another case it is M plus O2 equal to MO2. Now, oxide scale is this one, this is PO2 scale. Now, at this point, if I connect and extend, I will see that this is touching this particular point, and this indicates PO2, let us say, and this equilibrium TE. So, let us say this is the temperature axis 0 K, this is temperature axis, fine. So, now at this point both the reactions M plus O2 equal to MO2 as well as N plus O2 equal to NO2 are in equilibrium. At T equal to TE, fine. And we could see that, so since they have same for both the reactions, that is what if this partial pressure is maintained in a closed system, let us say in this closed system I have M, N, MO2 as well as NO2 and partial pressure of oxygen equilibrium T, this is maintained, I would see that oxidation, this process, both the oxidation reactions will reach equilibrium. But now let us say I take some temperature which is below TE, let us say this is T prime. Now at this temperature I could find out what is the equilibrium partial pressure for N plus O2. So, I can connect this point, I can extend and see where it is meeting. So, this is PO2 equilibrium T prime for NO2, I am just writing NO2, this oxidation process. Now, for this I can also find what is the equilibrium partial pressure. I have to just connect this point, extend it and see that here it is cutting. So, this is PO2 MO2 equilibrium T prime. Now, if I have a system where I have M, N and O2 at 1 atmosphere pressure, this is kept at T prime. So, then of course, I could see that both M, the first event what will be observed, M will go to MO2 as well as N will go to NO2, since these partial pressure and the 1 atmosphere partial pressure is here as per the scale. This is the 1 atmosphere PO2. Okay. So, now we could see that partial pressure of PO2 for MO2 or the formation of MO2 at T prime is less than 1 atmosphere of partial oxygen, and even PO2 for N oxidation or NO2 formation at T prime, this is also less. So, both these oxidation will start. Now, because this system would try to reach equilibrium, so once it reaches to this point, it will be satisfying the equilibrium condition for oxidation reaction N plus O2 equal to NO2. But this particular reaction has got much lower, since second event MO2 not reaching PO2 MO2, and here since Fine. So, oxidation, both the oxidation will take place, but this will, and one, since this is closed system where we are not allowing any oxygen to come in from outside or oxygen to come out from inside. So, the oxygen partial pressure would start decreasing from 1 atmosphere, and first it will try to reach PO2 this will be reaching this will reach. So, N plus O2 NO2 will reach equilibrium, and this will not reaching equilibrium. Why? Because fine, because of this phenomena, because of this situation, because since this partial pressure for MO2 formation is less than this, which are in equilibrium at T prime, that is what this particular reaction will reach equilibrium, because the oxygen partial pressure is gradually decreasing and finally it will reach here and it will reach equilibrium. But since this particular reaction, needs further oxidation and needs further reduction in oxygen partial pressure. So, that is what this will go on. And the third event is MO2 will continue till, since PO2 tries to reach T prime. So, oxidation of M to MO2 will take the oxygen content further down. Now, once it goes below this, fine. So, then it has to take more oxygen, that metal needs to have more oxygen to reach to this, but once it crosses this particular point around this region, oxygen is depleting, but metal M needs more oxygen for oxidation. So, this excess oxygen it has to get, where from it has to get that excess oxygen to reach this equilibrium condition, because already this has reached equilibrium once it has reached to this particular point. So, that is what NO2 will try to move to O2 plus N, and this oxygen will be supplied to this in order to have more oxidation, and that is what it is possible, that then only it will be possible to reach this partial pressure of oxygen in the system to tends to be PO2 of MO2 at that temperature. Fine. So, that means we could see once this particular partial pressure is achieved, this reaction reaches equilibrium, then in order to reach this reaction to reach equilibrium, that means the partial pressure attainment of this partial pressure, we need more oxygen, and that more oxygen will be provided by the reduction of NO2 to N and O2. So, this process will start happening. So, finally, it will reach here, it will reach in this particular location. So, and that will be the fourth stage, then M, this reaction will reach equilibrium equal to PO2 MO2 equilibrium temperature prime, and NO2 will keep reducing, will keep getting reduced to N plus O2. So, and if this happens, then we could see that my partial pressure of oxygen of the system will decrease and it will try to reach this. So, the final system will contain M, O2, N and M. This will be the final. Of course, I will have oxygen also, and this oxygen will be in equilibrium with these two, and N will be the product in that particular simple system, provided we have sufficient M. Okay. So, which will allow the oxidation, and N will be the final product. So, N will not oxidize, M will oxidize. So, this is the condition which can be set. This is the temperature I can set when I would like to prevent oxidation of N metal. And how can I do that? I have to have another strong oxide forming element which will have a much lower partial pressure of oxygen in equilibrium at that temperature where both M and N are there in that system. So, this is one way to decide which metal in at a particular temperature, which metal will oxidize and which metal oxide will reduce. So, this is a very good information we can get out of this particular Illingham diagram. Similarly, if I try to see a temperature, let us say here T double prime, what will be the product? You just do that similar process, you will see the final product would be NO2, M and O2, and of course, N, and I must have sufficient N so that metal oxidation for the metal M is prevented, and you have to do the similar operation. And but at this temperature I would have all those phases MEM, N, MO2, NO2 as well as oxygen, provided we have sufficient amount of M and N. Okay. So, this is about Illingham diagram, and one important information what we are getting, that to understand whether a metal will oxidize or not, we have to see that whether this particular we have to see the partial pressure of oxygen in equilibrium with that metal in that system. If it is more than the partial pressure of oxygen in equilibrium, then oxidation will take place. If it is less than the partial pressure of oxygen in equilibrium, then the oxidation will not take place, rather reduction of that oxide will take place. And also it tells us if we have two oxides, depending on the situation, that means depending on the temperature, I could get one metal oxide is getting reduced, another would keep on oxidizing, or the reverse can happen if we choose a different temperature, depending on where these two oxide lines are cutting. Okay. So, this is about Illingham diagram. We will stop here, we will continue our discussion in our next lecture. We will talk about kinetics of oxidation. Thank you.